Okay, thank you for everyone who is attending this tutorial. Welcome. So the Vortex is open source hardware and software for GPU, and we extended RISC-V ISS to support the Vortex. And then currently it is implemented tested on Intel FPGA, and we'll show a demo video of running Vortex code in Intel FPGA, and then currently Xilinx support is ongoing. And then we're also working on software stacks, and our mindset of this project is building an open source communities. So we are using only open source platforms for the compiler, runtime systems, and even ASIC type. And OpenCL is currently supported, a subset, and really a subset of the CUDA is currently supported. So this is today's tutorial schedule. First, I will give a brief introduction of GPGPU background. These are just for the people who haven't worked on the GPU. I assume most of audience of the tutorial already know about GPU, but just in case some are not familiar with the GPU, we want to provide some background. And I guess I forgot to introduce myself. My name is Ha-Seung Kim. I'm a professor at Georgia Tech, and we've been working on this project for a few years. And then we have presenters. Blaise Tyne, he's the main hardware architect for this project, who's been leading this work. And he will present the Vortex microarchitecture basic and cost structure reviews. And then Robin Han is leading a software effort, especially running a CUDA and OpenCL stack. And so Robin will present the software stack and OpenCL part. And Liam Cooper is our undergraduate students who've been helping a lot to set up this tutorial and also running a Vortex into the FPGA. So Liam will present how we run the Vortex and how and brief introduction about tutorials. And then we'll briefly conclude and some discussions, and then we'll move on to the hands-on sections that trying to provide the help on the tutorial. And other than the presenters, we also have Jeff Young, who is also organized and who is behind the scene of providing all the VM images and make sure these accounts are available. So I assume that Jeff will provide how to get the access. And then Santosh is also another undergraduate student who is helping us to organize the tutorial. Okay, so Santosh just posted out the tutorial GitHub link. If you go there, you will find the information about how to download the VM images. So we encourage you to download the VM images now because it takes some time. And then we also create a temp account just for the micro conference so that you can try out this Vortex. This one doesn't give FPGA access, but it gives all, it has all other source. It has all other tools that you can just download the Vortex Git repo only and you can try out tutorials. And if you need a account for longer than after micro, please send a request crunch Rose Gallery account. That information is also available in our tutorial GitHub. Okay, so then I will start the GPU background. I think everybody can ask the questions. Not sure you can actually speak. If you cannot speak up, you can type in the questions in our chat box. We have people who can look it up and convey that to the presenters. And we have a little bit of a formal presentation and the mixtures of this Q&A, especially we like to have some discussions about what would you like to see or on in Vortex project as you're at tutorial materials. So we like to have some more engagement about these tutorials. Okay, get started. Okay, sorry, I think the tutorial link was only posted into the panelist only, so I will post it again. Oh, okay, so Jeff will answer this question, so I will just proceed next step. So, oh, sorry. So I assume everybody actually knows about the GPU, but so I'll just give a very brief introduction about GPGPU background. So as you know, the CPU has a 5-stage pipeline, and in order to increase the performance on CPUs, we can go to superscalars or we can go to multi-threadings. Or that's how we improve performance on CPUs. Then GPU pipeline is something similar. It starts with something similar, but there are a few differences. One of them is it has a concept of work or depending on this company, you can call it wavefront execution models, and which is SPND program model. So same instructions will be executed by multiple threads, and then multiple threads are forming a work. And this diagram will illustrate we have a program, and it can have a multiple thread, and those will be grouped and they will be executed. And this is a brief overview of GPU pipeline. The pipeline itself is something similar to the CPU traditional pipeline stages that has a fetch, decode, register, and scheduling and the execution time. But in the scheduler part in the front end, it has a little bit more sophisticated because we have to choose among the multiple works, and then also the scheduler for this which work to execute or which waveform to execute, and this be also enhanced. And more importantly, the execution width is so wide, and that's where we get a lot of data level parallelisms. So the scheduling policy is within a thread. This is a static code will be executed in order, but because the warp will be executed any order that's a source operand already, when you look at the dynamic instruction traces, it might look like out of order executions. But if you look at within a warp, just in this case, within the same colors, you will see these instructions are executed in order. And the threading scheduling policies, there have been lots of research has been done to improve threaded scheduling policies. We've been only implemented a simple round robin in our Vortex, and then the other policy we could implement it easily is greedy than oldest policy. So round robin, when you have multiple works, we just rotate one at a time, whereas greedy than oldest, we execute the oldest one first until there is an event that prevents from execution further, such as a cache misses. In this case, it illustrates the memory accesses. In that case, we switch to another verb and then execute it again. And then you see another stalling event, then we switch it to another verb and so on. So there is a pros and cons. In the round robin mechanisms, it gives some more parallelisms. And when it has a memory cost, it actually improve the memory level parallelisms. But in this example case, the stall time is actually longer, whereas in GTO, we start generate memory cost much earlier, so that it looks like the stall time is shorter, but it is not utilizing all the memory bandwidth. So there have been many research to improve this thread scheduling policies to get the right balance between these memory level parallelisms and reducing the stall time. And then probably the biggest changes in terms of area and is the GPU architecture, even in our Vortex architecture, is having a large register files. And then one of the biggest characteristics of the GPU is it can support many number of active threads that requires having a large register file. So for example, if you have 128 threads and 64 registers, then we need to have 128 times 64. And so the oldest GPU architecture, oldest GPGPU architecture, I would say, that G80 architecture has 64 kilobyte register file, while at that time the cache size was only 16 kilobyte. In the Vortex, we are using a RISC-V ISA, so unlike NVIDIA architecture, per thread register file is fixed because it was coming from the RISC-V ISA. So 32 registers times number of threads per warp and number of warps, and the number of cores will be the register file size. And typically design register file in GPUs are very challenging because in order to support this high throughput oriented computing, that we need to have a lot of register file read, and typically 2 read and 1 write is needed. In a Vortex case, a little bit easier. I would say they're a little bit easier than NVIDIA GPU architectures because we have a fixed number of registers per thread. Again, because it's coming from the RISC-V ISA, so we can easily bank the register files. So if we can easily bank the register file structures will be something like this. We conceptually, we can think that each of the threads have on one bank of the register file, and then we can access the 2 reads and 1 write per bank, and then this will be stretched go to each of the lane. So that when you index the register files, we index with the register IDs and warp IDs or thread IDs. And handling branches, so even though it's a data pair architecture, so it still needs to handle the branches. For example, this is famous CUDA's reduction examples that we were trying to compute the reduction of the values. First, we have all the thread items available, and the next layer only the even numbers are computed, and then only the multiple of 4, multiple 8 will be computed. So that during this period, their other threads were just waiting, doing idle. And in this case, at least all the threads are going the same path, and just some threads are being idle state, but we can also having more complex if and else state that other threads will go to perform some other work. So handling these branches in a GPU architecture was the first main research problems that people have to work on, because this is probably the most challenging part that compared to SIMD star architecture when you're trying to move to the SIMT, single instance multiple thread architecture. And the branches that are going into the different paths is called the divergent branches. So there are a few ways, and like this kind of research was mostly done in before 2010 as a really early GPGPU architecture research that people have worked on how to reduce divergent branches. And our approach is that we have a split and join, and these handling divergent branches are probably the biggest ISA extensions that we have to do in order to make a RISC-V ISA to support a GPGPU. And details of this IA support and Vortex architecture will be discussed in the later sessions. And here I will just give us a context. So we used approach of the compiler inside split and join instructions. And then when there is a split, we put the T-mask in IPDOM stack. And then next PC address will be in the stack. And then once you finish the work, when you reach the join point, which is the IPDOM, that will pop up from the stack. And there have been many GPGPU programming. Originally, it started with the CUDA. And then OpenCL was trying to provide a more unified platform and supporting various other platforms. And then each of these major vendors also have their own version of GPGPU programs, such as HIP or DPC. And then OpenMP extension supports the GPU program. And there will be more are also coming out, as I even found that RISC is trying to support the GPUs. And I will also provide a quick summaries of the CUDA. Again, people who haven't worked on this field, these are really the basic materials, but I want to also provide context for the people who have not done any GPU research. So in the quick summary of the CUDA program model is somewhat based on single instance multiple data, but because it allows the divergent branches, it becomes a single instance multiple thread. And in a set unified memory space, and the program hierarchy is thread and block and kernel. And this is a CUDA programming examples that shows matrix multiplications. This is a little old style programming example that has an explicit host code and kernel code are located in separate files, but recent CUDA, these all be inside in the one single CPP file. And so the basic idea is there is a host code that launch the kernel, that matrix-small kernel, and it specifies a number of threads per block and number of blocks per kernel. that it provides the information. And then these kernels are launched, and then once the kernels are launched, every single thread will execute the same code within this kernel. And that's where this SIMT shows up. And the execution model-wise, these threads form a warp and multiple. The warp is a hardware concept. It was originally really be a microarchitecture concept, but people have utilized this warp for performance optimizations. And nowadays, this warp itself is really exposed as a program model, so that warp is a part of the program model that specify how many threads within a warp. And originally, this was proposed as 32, and the warp size could vary. But whereas now, the warp size is, since it's exposed program model, that needs this 32 needs to be specified by the program model as well. So there is a warp will be executed, and it goes to the shared memory. And then there is a multiple thread blocks. And to just make an example simpler, we just assume that each of the CUDA block will be executed and separate the CUDA cores that will be within the CUDA cores. That NVIDIA's term is a shared memory, and in Vortex, this will be a core too. And then within the core, there is a multiple stream processors, or it could also consider as vector units. Vector lanes will be there in this to execute this thread. And even though the entire block will be located one CUDA core, we'll need to execute one warp at a time, and the warp sizes can vary in some sense by microarchitecture. And if I compare the GPU versus the CPU, local memory in its GPU is similar to the stack in CPU, and shared memory in the GPU is similar to CPU's discrete memory space. And then there is a global memories, a central storage, and the CUDA has a constant memory, text memories are exposed for a model, whereas OpenCL didn't. And then constant memory is read-only structures, and texture memory is read-only, but it's more targeting for larger size compared to constant memory. And more importantly, this is trying to support the 2D structures, which are commonly used for graphics applications. And this is showing how you declare the shared memory. So shared memory is called shared memory, but it is a scratchpad memory. And also still use the term shared memory in our Vortex documentation, and that's what it means as a shared memory. And when you execute this CUDA code, it follows the SIMT execution model. And so each of the thread has their own identity, the ID numbers, and also block ID. So each of the thread, even though they're all executing the same code, because each of the thread can have their own IDs, this block ID and thread IDs are using that, it can access different elements. So if you want to add two vectors, 16 elements, then each of thread is just simply index the block this element by combination of their own block ID and thread ID. So having this block ID thread ID is also crucial to support GPU extensions for Vortex. So we also use special registers to support this thread and block IDs. That's also another important component of RISC-V extensions. And then when you end the simple CPU code, which is iterated, becomes in the CUDA code, and this loop is just showing as only one, because in a simple example, 100 threads we just executed each of the loop iteration. And because this thread and block IDs are there, we can index the memory location instead of II. We can just use some constant times block ID plus some constant time thread ID to get each of the elements. So if it's depending on 1D, 2D data structures that have a different just formula to index arrays. And then CUDA used the Burke synchronous parallel program models. That's also what we've been using in Vortex. Later CUDA versions have string features and other advanced features, but we haven't got to that support in our Vortex yet. And it's a simple comparison between OpenCL and CUDA, because OpenCL benchmarked CUDA, so they have a lot of the common features, but there are some slight differences. And currently, Vortex mainly developed for OpenCL, but because of these similarities, we are also extending to support CUDA. Okay, so this is the end of the first introduction of the GPGPU architecture. Now I'll hand it over to Blaise Tyne. He's a PhD student at Georgia Tech, and he has been the main hardware architect for this project. And if you have any questions, please post in the Q&A in the chat box. Okay, thank you. And after the students, after this presentation for each of the sections, I will come back at to discuss the conclusions and also any more open Q&A or suggestions. Okay, thank you. Places are yours, and we cannot hear you. So if you're muted, please unmute yourself.
Hello?
Yes, we can hear you. Thank you.
Thank you. My name is Blaise Tyne. I'm a member of the Vortex team. Thank you for attending this workshop. So I will be presenting the Vortex microarchitecture. The agenda for this presentation is I will go over the IXA extension, and then we talk about the GPGPU microarchitecture, then the description of our high-level bandwidth caches. Then we will go over the additional tester unit hardware that is part of Vortex. And then I will end with some demonstration of how an OpenCL kernel is mapped into the Vortex hardware. A high-level description of the overall Vortex platforms includes a software compiler and hardware stack. The complete GPU currently scaled up to 32 cores running at 200 megahertz. It is a PCIe-based GPGPU, so the application, the OpenCL application of CUDA runs on the host, and we use PCIe to transfer the kernel and the metadata to the GPU. So it operates similarly to AMD or NVIDIA GPU. It integrates caches, integrates a shared memory, floating point unit, and the additional hardware texture unit. We have tried to make the entire platform open source. OpenCL that we're using is open source. The driver stack is also open source. The RTL simulator, as well as the synthesis tool, we support actually USIS as well. But you could also use Quarters as well. The ISA extension that we added to on top of RISC-V to support Vortex covers four categories, I would say, of SIMT features. So we support wavefronts, we support threads, we have support for global memories and shared memories. The register file has been extended so that we can add support for the number of threads and wavefront. We have synchronization instruction as well added, and that all falls into 6 new instructions. WSPAN, TMC for thread control, a split join for control flow divergence, the barriers, and the TEX for the texture sampling unit. This is the baseline microarchitecture of a RISC-V pipeline, 5-stage RISC-V pipeline, where you have the fetch stage, the decode stage, the issue stage, the execute stage, and the commit stage. This is an in-order issue, out-of-order commit pipeline. The first thing that we did was to extend the pipeline so that we can introduce the component to support SIMT. In the first stage, we introduce a wavefront scheduler to schedule instruction into the pipeline, and also associate instruction with the wavefront and also a thread mask. In the issue stage, we expanded the GPR, the register file, and we also introduced an instruction buffer. And in the execute stage, we have a GPGPU unit that was added to support the 6 new instructions that was added into the ISA. And in the execute stage, we also have the texture unit. The microarchitecture is scalable, so we are able to scale up to a high number of cores, and we have a hierarchical structure that allows us to kind of group cores together into clusters. This allows us to actually support L2s and L3 caches. So at the highest level, where we have the processor can have multiple clusters, all that can optionally be attached to an L3 cache. And each cluster can have a certain number of cores attached to them, and also connected to one L2 cache to access memory. The entire processor on the FPGA needs to communicate with the host via PCIe. It also needs to access the local DRAM memory. So we have a command processor. It's a separate unit that is sitting on the FPGA board. It's RTL component, and it manages the communication between the host CPU and the processor itself. It's also used to handle communication between the host CPU and the local DRAM. So in general, when a kernel is executed on the platform, the host will use the command processor to push the kernel to upload the GPU kernel into the local memory, and also to upload the data set that is used by the kernel into the local memory. And then it will start the execution of the processor, and the processor will read data from that local memory, process it, and then write the result back into local memory so that the processor could read it back. So these are all the activities that are taking place inside the command processor. A typical execution of the Vortex instruction will start in the first stage, where we issue an instruction with a PC WID, that's the wavefront ID, and then a thread mask for all of the threads that are active. And the instruction we get into the decode stage, and the instruction will be fetched from the instruction buffer, and then we will have an instruction. The warp ID will still be kept, and also the thread mask as well. And this information will be sent to the execute stage. We have an instruction. We have the register, the register values, the wavefront ID, and the thread mask. And then once the execution is complete, we now have the result, the wavefront ID, and the thread mask. The wavefront ID and the thread mask is actually used to update the register file, because there's a separate register per thread, and also there's a separate register per wavefront. The Vortex high bandwidth caches It's a non-blocking cache, and it is highly configurable. It's one of the challenges that we encountered while implementing the high bandwidth cache was to figure out a way to scale the design for the hardware, for the FPGA, being able to leverage the available SRAM and the constraint with the number of ports that exist on the device. There was also a challenge with handling bank conflict in an efficient way, so that we don't introduce too much area cost or performance latency. The traditional approach of handling bank conflict on the standard GPU is to implement memory coalescing for aligned addresses. And this generally takes place inside the LSU unit. This presented some shortcomings when it comes to Vortex. Implementing memory coalescing in the LSU made it so that it created an interdependency between the LSU and the cache. The current cache implementation that we have is templated, so we use the same cache for the same cache template for the L2 and L3 is fully configurable, and creating a strong dependency between the LSU and the caches makes the design quite complex. The other challenge was the overhead. The overhead of doing the memory coalescing in the LSU unit. He introduced an additional latency. The other overhead was on the area, because now if we have to do memory coalescing in the LSU, we have to propagate the extra metadata associated with the coalescing all the way through the L1 cache. The other thing was the shared memory doesn't require memory coalescing. And also we needed to also support memory coalescing for L2 and L3 caches. We needed to support we need to support bank conflict handling for L2 and L3 caches. So the solution that we took was to implement multi-porting. The idea behind it is to allow ports to, so requests that are going to the same line are using the same, basically are using a separate port to that bank. So now if there is a, if a multiple requests hit the same bank and they happen to hit the same cache line, then we use a separate port inside that bank. And this allows us to, with this change, we are able to include the bank selection, the memory coalescing as part of the bank selection and the bank arbitration. Like you see in this on this diagram, there is a pipeline register between the request stage and the tag access stage, and everything before that takes place in one cycle. And the advantages that this provides us is the fact that we don't have to add an additional port on the XRAM. On the FPGA, you are limited to only 2 ports, and we're using that for read and write. The other advantage is that I already explained there's no additional latency overhead with this approach. We can share these features for L1, L2, and L3. It doesn't have to be only placed on the only supported for L1 caches. The other advantage is the fact that on the FPGA, the memory bus, the data bus of the memory is generally 512 bytes. And if we want to export the full capacity of the memory bandwidth, we also need to have the cache line to be at that granularity of 512 bytes. But now, if we are using a large cache line and the data bus for the actual processor is 32-bit, there is a kind of a waste. With multiporting, we can basically leverage the entire bandwidth because we can have multiple ports now accessing the same data. The other hardware extension was for the support for texture unit. Texture unit has an important it's an important part of the modern GPGPU today because it is used for image processing and as well as for 2D and 3D graphics. It's a memory bound and also compute bound operation. It's memory bound because you have the operation access a lot of pixels. And sometimes the access pixels are different layers of the textures, like mid mapping. It is compute bound because there's processing that takes place, the texture filtering that takes place once we access the data from memory. We have to filter, we have to apply some filtering operation before to obtain the final image. The hardware design for the microarchitecture for the texture unit uses the CSR to do the programming. So we store all of the state of the texture unit inside the control status registers. And we use the CSR instruction to program the state of each texture unit. And some of these states include the dimension of the texture, the format, the addressing mode, the filtering mode. And this configuration is done per texture bitmap, basically per texture layers. The pipeline of the texture unit once the GPU send a request for a texture operation. In general, you will have a UV coordinate for the texture and also a level of detail, the LOD, which is basically the layer in the texture where to fetch the texture value. And this goes into the address generator, which is the first component in the texture unit. And then once it reaches the address generator will generate all of the memory addresses that are needed to retrieve the text cells. And that will go to the memory scheduler, which is part of the texture unit. And the memory scheduler will be the one scheduling all of the memory requests to memory, and then also receiving the memory block back and doing the memory reordering before sending the final text cells to the sampler stage, where we first decode the memory data, the text cell data. We decode it based on the texture format, and then we apply the appropriate texture sampling. So here I'll be describing how we map a typical OpenCL kernel to the Vortex hardware. The OpenCL distribution work item distribution is organized in a hierarchical structure where you have a work group, and inside the work group you have work items. OpenCL provides you the ability to control the local size, the size of a single work group, and then also the number of work groups in a grid fashion. there are two main APIs that are accessible inside the kernel, get global ID and get local ID, where you pass the coordinate of your specific grade. And get local ID gives you the index of the task at the workgroup level, and the local ID is at the work item level. This is a typical, this example shows, it's actually a SGM kernel written in OpenCL, and you can see the global ID. We're using the global ID here to retrieve the row ID, and we're using the global ID with the value of 1, which is the Y coordinate, to retrieve the column. And the parameters of this kernel includes the source buffer, which is capital A, the two source buffer A and B, and the destination buffer C. So what happened in the compiler is we take the specific kernel, and then we create a wrapper around the specific kernel. Vortex will distribute the work group, the global size. We distribute that among all of the threads. So basically, the work groups are basically spread among all the threads available on the device, and we use the priorities based on the maximizing the wavefront capacity, meaning that we try to fill all the wavefront during this distribution. And the algorithm populates the global IDs X, Y, Z for the kernel. And the API VS Spawn kernel, we launch the kernel wrapper with the global identifier. And inside the wrapper, we have inline loops. And these loops are the loops that implement the work item scheduling for the local IDs. And there is a context that is passed through the wrapper that allows us to retrieve the argument for the kernel. And then we can call the kernel at the bottom. That will be all for this part of the presentation. Thank you. So I will be moving to the other side. Let me see how to close this.
Blaise, you're also still the next speaker for the code review.
Yes. So I will be the next speaker for the code review section.
Yes. So you can just continue.
So I will jump to I will stop this one. So I need to close. Stop share. Okay, great. And switch to the other slide. Start. Okay. So let's share again. Good. Okay. So this is going to be a little longer presentation. So I will be going through the structure of the current core base that we have. We described a little bit what the source tree looks like, where we have documentation, the section where we have the hardware code, the synthesis, simulation, the runtime, the driver. And I will also go over the testing source tree and also the continuous integration portion. And I will also describe a little bit how we configure a particular execution of Vortex, either for synthesis or for just running simulation. And then talk about the coding convention that we use in Vortex. The source tree, this is a snapshot of, it's a simplified snapshot of the existing source tree that you have on GitHub. But at the high level, we have a folder where we place the continuous integration scripts. We have the documentation included in the doc folder. The hardware is in the hardware folder. The runtime, the driver, the simulation is under the Steam. So Vortex has a couple of simulators. I would say in total we have 4 simulators. 3 of them are located here, and the other one is part of the FPGA simulation. And then the test source tree is the last one. In the documentation, the main entry point of documentation is Vortex markup file, vortex.md. And then there are other markup files for the code-based layout, the microarchitecture, the cache subsystem, the software, the simulation. FPGA separate guys provide information how to set up the Intel-Altera FPGA. And then the last one explain how to debug Vortex when you're running in simulation mode, or if you're running on the FPGA, how to enable tracing and actually read the logs. In the hardware section, this is under Vortex_W. We have a folder called DPI. This is where we place all the Verilog DPI library. We extensively use DPI, Verilog DPI feature to speed up for enabling tracing of the entire code base, but also more importantly to speed up the execution of Vortex when you're running in simulation mode. Some of the components like the floating point unit, we have a complete full implementation of the floating point unit in DPI mode. And we also have integer multiplication is also implemented as part of the DPI library. This is to make it so that when you run Vortex on your local machine, but you can of course you can disable those through the configuration. You can decide, oh, I want to have the simulation run fully RTL, but generally for us it's not really that important to simulate the floating point unit, for instance, and it's very slow. We also have a folder where we put all the scripting tools for the hardware. There's a folder where we have the synthesis. We have several synthesis targets. They're all located in the synthesis folder, and we have some unit tests for hardware components. The RTL code base include the AFU, the command processor that I described earlier in the previous presentation. There's a folder where we have the cache source trees. The FP cores is where we store all the floating point unit cores. We have a separate folder for this because we have I just mentioned earlier, we have a DPI floating point unit core, which is based on the Verilog DPI interface. We do have an RTL implementation, and we have an implementation for the FPGA, where we use the Altera hard block floating point units. The texture unit is under the texture unit location, the interfaces. This is where we place all the interfaces for Vortex. In the last section, when I talk about the Conde convention, I will be talking a little bit about why we heavily using interfaces in the platform. Libraries are where we place all the shared components. An example of a library could be like a FIFO module. This is the dependency tree of the processor. This is useful if you are doing RTL design and you want to kind of see what the module dependency looks like. And it also helps if you are looking at the trace, the VCD trace for the waveform, and you kind of want to navigate and look and find where you want to expand your trace. So at the high level, you can see that this is actually very similar to the pipeline that I showed in the previous presentation. At the high level, you have Vortex here. This is a processor. There's a module, high-level module for Vortex that represents the full processor. And inside this module, there are a couple of modules for the cluster. There's an array of cluster module, and inside a single cluster, there's an array of cores module. And a single core, we have two modules, one for the pipeline and one for the memory unit. And in the memory unit, we have the D cache and the shared memory that are part of this block. At the pipeline level, we have a separate module for the different stages of the pipeline. So we try to be very explicit with the naming convention here so that it makes it easier to recognize different pipelines. In the commit stage, we have the write back. In the issue stage, the scoreboard, the GPR register file, decode has the instruction buffer, and fetch has the iCache and the scheduler. And in the execute stage, we have the execute unit, the ALU, the LSU, the FPU, the control status register unit, and the GPU unit. This is where we have the implementation of the ISA extension for those six new instructions. The FPU, which is the command processor, this is the part of the hardware that enables the communication between the CPU and the actual processor. And these are some of the components that are part of the command processor. The AVS wrapper is the component that converts the memory request coming from the processor into the Avalon interface. This is the Altera memory interface. We have a scope analyzer for debugging the FPGA that is also located inside the command processor. The CCI to memory request is the component that converts the memory request to CCI is the communication that goes to the PCIe, the PCI interface. In the cache, the folder where we store the cache implementation, there are several components that are part of the cache data structure, the cache code base. At the highest level, we have an NC bypass. This is for bypassing the caches. Vortex allows you, there are some memory addresses in Vortex that allows you to bypass the cache completely and go to memory. For instance, if you need to print, if you want to print something to stand it out, we don't use the cache for the standard out address. So this component basically redirect requests coming from the LSU unit directly to the memory. The flush control block is the component that actually flushes the cache. The bank selection unit is the unit that selects which bank the request should go to. Of course, we have the bank, and then the response merge is the component that retrieves the output of the bank and then redirect it back to the core. And inside the bank, you have the DAC access, the data access, and then the MSSR, which are also components, separate module included inside the bank. In the synthesis folder, this is where we have all of the different synthesis backend. OPE is the one that we use for the FPGA synthesis. We also have a quarters folder where this is more for synthesizing RTL. In most RTL project where you are interested in doing area or performance optimization, you will be using this the build script located on the quarters. Here you are not really creating the bit stream. You're only synthesizing the RTL, whereas here you're actually creating the full FPGA bit stream. So it includes the processor, it includes the command processor, and it also includes the Intel FPGA components. So it's a much larger bit stream that is generated here. We have the folder where we have Yosis, Synopsys, and Mulder Sim as well. Under the simulation tree, we do have the RTL sim. This is the main RTL simulator, processor RTL simulator. This simulator is only the processor with the cluster and cores and everything inside, but it doesn't have the command processor. This is a typical simulation that you will do if you are trying to simulate Vortex in a SoC environment. Whereas here, the VLSIM is the one that actually includes the command processor, where you say this is more like a simulation where you need to involve the host operation as well, like a PCI-based environment. And CMX is our circular approximate simulator. In the runtime tree, we have two main folders. We have the linker folder where we drop all the loader scripts, and we have a source folder that includes a library where we include all the startup routine. When Vortex kernel start the execution, we execute the startup routine to initialize the stack pointers and all many other things. The global initialization for C++, and we also have a library for printing, for handling printing to standard out. We needed to implement our own here because Vortex runs with multiple threads, so we have to synchronize the print to standard out with our own library. It's exactly the same interface to printf, but the implementation is different. The scheduler we have, this is where we include all of the API call for kicking off the execution of tasks or the execution of kernels. This is where we have all the library that implements the performance counter logging. And then the system calls. These are system calls that we redirect into Vortex, for instance, if you want to, many of the system calls that are part of the C library. And in the driver section, so a driver in Vortex, that's the component that enables the communication between your application and the processor. We have a common interface for our driver API in Vortex. So we have different implementation of the driver, but they all follow the same interface. The stub folder is where we have the kind of the stub library that the application should link against. It implements the driver interface, but the actual implementation is empty. This allows you to compile your application And then once the application is already compiled, you can change the actual driver implementation behind, basically by replacing the library that it links again, and the application will still run. So a compiled application, if you want to run that application without having to compile it again and run it on the FPGA, you just replace it with the FPGA driver. Or if the same application, you don't want to run it on the FPGA, you decide you want to run it on let's say the RTL sim simulator, you replace it with the RTL sim driver. Using this interface allows you to make it easier to run a program either in simulation mode or in cycle level simulation mode, RTL simulation mode, or actually FPGA mode. It creates some form of it makes it possible to truly validate the result regardless of the driver implementation that you're using. In the test coverage tree, we have a runtime folder where we have the main runtime test. The regression folder implements the C++ applications that we run. Some of these C++ applications have kernels written in C++. And in the OpenCL folder, these are actually OpenCL benchmarks that are located here, and the kernels are written in OpenCL. And the RISC-V folder includes the standard RISC-V test. These are the RISC-V conformance tests that all RISC-V compliant processor should execute. In the integration folder, so we have, I mentioned earlier that we have a continuous integration support for Vortex. This allows us to run regression suite anytime we commit changes to the code base. It also includes some useful programs like the blackbox.sh. This is the main, I say, test runner application in Vortex. It basically allows you to run pretty much every program that is part of the code base. It gives you the flexibility to configure how you want to execute that application. You can use this application to change the driver or to decide whether you want to enable L2 or L1 cache. So this is what we use for pretty much executing everything. The regression script is what is running on the server during the continuous integration test. And this one basically executes all the tests in the code base, including the compiler tests. For this one, deletes all the compiled kernels, rebuild them again, and validate that they're correct. We also have some script for generating pre-built binaries. We have, I mentioned earlier that we have our own, we're using an open source OpenCL compiler and runtime that we modify for Vortex. So you can use this to rebuild the binary that you need, and you can also use the toolchain install script to install precompiled binaries. This will install all the dependencies on your machine directly from our own, by taking them from our own server. It supports Ubuntu 14 and also CentOS 7. And you can pass the command line _help on all of those components if you want to get some idea of what the command line options are. Now we'll be talking about how we configure Vortex. In the hardware folder, we have a file called vs_config.vh. This is maybe the most important file in the code base because it is used by the hardware, by the runtime, and also by the software, by the simulator, and also by the driver. It's run pretty much by every single component in the code base. This file is a very log header file, and inside this file, we define many of the parameters that are used to configure the processor. When you set up Vortex for the first time and you run make, we have a Python script that converts this Verilog file into a C++ file with the same name, but the extension is different, and generate the same configuration file so that the driver, which is a C++ program, the runtime, which is a C++ program, and all the simulators, which are also C++ program, can use this to figure out exactly how to configure the specific build. And inside the VS-config file, there are several components. So I've only selected a few and kind of organized them in a way that makes a bit more sense. So the structure section of the configuration file allows you to like select the number of clusters, cores, the number of wavefronts, the number of threads, barriers, whether you want to enable L2 or L3. There's also a section for the memory. The section for the memory, if you want to change the memory block size, the L1 block size, if you want to change the startup address of the program, if you want to change the IO base address, this is the standard add base address. So even the CSR's locations. So all of those can be changed in the configuration file. We also have the CSR addresses as part of this config file. One of the reasons why this is not really something that you want to change, but the reason why it is added to the configuration file is so that it also gets generated inside the C++ version of the file, so that the C++ component can actually know the values associated with each of those CSRs, mainly for the simulators. This forces us to have a strong conformance between the RTL and the simulators, and we won't have to kind of maintain different databases in each different components. The caches can also be configured. Here you have, this section only shows the configuration values for the Vcache, but we do have a section for L2 and L3, and also the iCache, including even the share memory. The share memory also has a section where you can change several attributes of the hardware. The software. So once you run the make that I described earlier, this file will be generated. And once this file is generated, the Vortex runtime and all the simulators can leverage the information included in this file. Here I show an example of the Vortex black box, of how you can configure the execution of an application vector add, where you can set the number of core to 2, the number of warps or wavefront to 2, and the number of threads to 8. This information actually behind the scene, this information is translated into a configuration script. So you can run the same script by passing the configuration as a command and argument like this to make it easier for users, or you can actually do it manually by actually passing the configuration information directly using this method. This method allows you, not everything can be passed in the command line in this way, but using the second method, you can pretty much pass everything that is included in this file. And the black box tool will basically rebuild the driver and the hardware to make sure that it matches the configuration that it needs before executing the program. An example here is you could just the memory latency. This is something that is used by the simulator. You can so not only you can pass information for the driver, you can for the RTL that is included here, but you could also pass information for the simulator as well, like increasing or decreasing the memory latency, for instance. For the synthesis, we use the same kind of the same programming model. The config.vh is used for building is used by the build script as well. And when you run the synthesis, if you want to, let's say, build the FPGA with 4 cores, you can use the configuration, the same syntax to specify, let's say, the number of threads that you want to use for this specific configuration. On the FPGA side, we explicitly have to specify the core as part of the build token, because it's a little bit more complex there's many other metadata associated with the specific core for the synthesis. But that's the only thing that is explicit when you are issuing MIC. But everything else is passed as a configuration. Like, for instance, if you want to enable the performance counters, you can actually specify it here. For the RTL interfaces, so now I will be talking about the coding convention that is used in Vortex. And I think earlier I mentioned that I will be talking about interfaces in Vortex. We extensively use interfaces to allow a component within the code base to communicate between each other. And we are enforcing a convention of master slave. So the mode port, for those who are familiar with very long interfaces, the mode port can basically have any name you want. But to be consistent inside the code base, we are explicitly using master for all outgoing signals from the interface, and the slave for the incoming signal through the interface. And grouping related signals inside the interface makes it easier for the reader or for new student joining the project to make sense of the hierarchy inside the code. Vortex extensively use the elastic pipeline pattern, just for handshaking within the code base. We're using that when we send a request from the fetch stage, when the request leaves the decode stage, when the request leaves the issue stage. We're even using it inside the cache itself, the cache design. So we try to maintain this consistency so that when you work in the code base, it is much easier to handle handshaking, because this is one of the challenging aspects of RTL design. If it is not consistent, then it makes it difficult to debug the code. And the way we implementing the LSC pipeline pattern in Vortex is generally you will have a ready and valid signal as part of the interface, and then you will have a metadata associated with that. And in this specific example, the metadata could be the PC value, and then also the wavefront ID. The other part of the coding convention is the standard that we use for naming the different files inside the code base. This makes it easier for self-documentation. In general, the rule of thumb is you don't want anybody to go through the documentation. If the code is well written and use a good standard, then it's easier to actually just navigate it without having to read the documentation. The other thing is it makes it easier for refactoring the code base because you can actually run a Python script on top to make changes that affect different aspects of the code base. It makes it easier also to extend individual components once this is consistent. So here I have some example of how we're enforcing the coding convention, for instance, for the modules, for the interfaces, for the headers, and also for the data types. We use it like if you're using struct or other data types, we basically have a way of enforcing the structure of how you name these files. And that will be all for this part of the presentation. And thank you very much.
Okay, thank you. So the next presenter will be Robin Han. Robin, I believe if you can stop share, then Robin can start to share. Robin Han is the first year PhD student. So he has been leading the effort of supporting CUDA on a Vortex. And so he will talk about, and also working on the software stack. So he will talk about 2 consecutive sections about the software stack and running on OpenCL and CUDA on Vortex.
Okay, so can you hear me?
Yes. We
Okay.
can see you and we can hear you. Okay, go ahead. Thank you.
Okay, thanks for the introduction from Professor. And hello, everyone. I'm Robin. I'm the first year PhD student in Tech and also in Vortex team. And first of all, thanks for all of you interested in Vortex project. And in this slide, I will introduce the Vortex software stack for how we interactive with Vortex hardware and how our software programs be compiled and executed on Vortex. And here is the agenda of my introduction. I only put some basic introduction in this slide. And for more detailed information, I put them together with the introduction of how to executing OpenCL and also POCO programs on Vortex in the next section. So it will be 10 minutes later. Okay, so first of all, for Vortex software, we highly depends on another project, POCO. POCO is just an implementation of OpenCL. In other words, it can support executing OpenCL programs on different hardwares. It consists of 2 parts, compilation parts and runtime parts. And for compilation part, it's based on LLVM. So it implements a series of LLVM translations or LLVM paths to optimize the input OpenCL programs. It can support several backend devices, including NVIDIA GPU, x86 CPU, and even for some customized accelerators. Besides, it accepts not only OpenCL programs, but also SPIR-V binary input as input. And to execute OpenCL programs on a backend device, first, POCO will compile the program and link the programs with hardware-dependent runtime library. And also, POCO has implemented some hardware-independent library, needed for some mathematical functions like sine, cosine, tangent, all those functions. And then after we got the compiled kernel, the POCO runtime, we use the device drivers to control the device. And so it will using the driver to allocate memory, do some memory copy, and also send the compiled kernel to the device and launch it. And finally, after we finish the execution on the device side, we can using the driver to fetch the memory from the device side to the host side. And so this is a whole process of how POCO executing our programs on a given backend device. So thus to support Vortex as a new backend to POCO, we need to care about the following parts. For the Vortex, for the compilation part, we have to care about the Vortex runtime for the POCO compiler. And also for the execution part, we need to do some modification for the POCO runtime part, and also we have to provide POCO with our Vortex driver so that POCO can use it to interact with the Vortex backend. And so for the Vortex programs, they have different interface as other device. Thus, we cannot directly using the original POCO compiler because it will generate an interface which isn't satisfy the requirement of Vortex. Thus, we have to modify the original POCO compiler so that they can generate the interface as POCO needs. Besides, Vortex has some specific built-in functions, like how we get those, do some warp scheduling or other things. So for this specific built-in functions, we have to implement those functions in Vortex runtime libraries. And this library will then link with kernel at compilation time. For execution, we need to provide a Vortex driver for POCO runtime. So to integrate a new device into POCO, we have to implement some basic operation like memory copy, memory allocation, kernel launch, and so on and so on, and put all those functions into Vortex driver library. And so finally, at the execution time, POCO can interact with POCO with Vortex backend device with the Vortex driver library we provide. So among all those software stacks, one of the most important part is scheduling, as we know how to map the computation to hardware resource is critical for achieving the higher performance. So in OpenCL and also in CUDA, work item distributed among work groups. However, as for Vortex, instead of work groups, we use waveform to be the basic unit for schedule. So a waveform is a group of work items, and the work item within one waveform are executed in parallel and also in locksteps. So in Vortex, we use waveform as a unit of scheduling. And we know NVIDIA GPU has a similar concept as waveform, and in NVIDIA, it names warp. And for NVIDIA's warp, it has the constant fixed size. It is 32 threads within a warp. However, in Vortex, warp size, or in other words, the waveform size is configurable. So although this feature makes Vortex more flexible, we have to put more effort for the scheduling algorithm because we have the configurable size of the waveform. So if you have, although for most high-level users, you can just execute Vortex without worry about those configurations. However, if you have any interest in changing Vortex software stack to achieve higher performance, I think this concept is really critical for you. So finally, in summary, the whole Vortex software stack is the library needed to integrate Vortex into POCO. So it consists of the Vortex runtime and the Vortex driver. And also we have to do some modification for the original POCO framework. So now let's go through the process of how to execute our programs on Vortex. First, we compile the program with POCO compiler. And inside the POCO compiler, the Vortex runtime library will be linked with the compiled kernels. And before we generate the binary, as Vortex kernel has different backend interface, we have to using device kernel translations to translate the kernel POCO generated programs into our own format of programs, which has the given interface POCO needed, Vortex needed. So after that, we can get the device code. And then finally, at the execution time, POCO will using the Vortex driver to communicate with Vortex. And then it will send the device kernel generated in the compilation process to the Vortex backend device, and also using the Vortex driver to launch the kernel and do some memory movement from between the host side and the device side. So this is the whole process of the POCO execution on Vortex backend device. Okay, so that's all. Thanks for listening. And if you have any questions, please feel free to type it in the chat box. And for further information, soon I will represent how to executing some special case for OpenCL programs and also CUDA programs on Vortex device. So now let's move on to the second section of my representation. So how can, okay, stop sharing. Okay, so in this part, we will introduce how to execute exactly project source code for OpenCL and CUDA on our Vortex GPU. So first, let's have a review of the POCO Vortex software stack. Although I just introduced it in maybe 3 minutes before, but in case someone is just jump into our tutorials. So in the first, as I said before, it consists of 2 parts for compilation part and also runtime part. And for a given input, we have to first using POCO compiler to compile the source code and generate to RISC-V binary file. And in the execution part, for the POCO framework, it will load the binary RISC-V binary from the memory, and using Vortex driver to send this up to upload this kernel into the Vortex backend device, and then using other functions in Vortex driver to launch the kernel. So this is the whole process of the POCO execution. And now let's have a look how to execute it on RISC OpenCL backend front-end language. So first of all, as I said before, the POCO is just an implementation of OpenCL. So it is quite straightforward to executing OpenCL with POCO. So first, I list the whole process, whole step we needed to do for executing OpenCL on Vortex. And first of all, assuming we have input programs, and it consists of 2 parts for the host programs and the kernel programs. So in the first step, as I show in the right stream, we have to compile OpenCL kernels to RISC-V binary. And in this step, we have to use POCO compilers because we have to do some kernel device kernel translations and code genes. However, as the original POCO do not support either the RISC-V binary, RISC-V architecture, not the Vortex backend device. So we have to do some modification for the original POCO compiler. And so this is the first step. And then after that, we can get the POCO kernel device. And however, from before our POCO, our OpenCL will executing the kernel as a texture field. But now after the modification, instead of the texture field, the kernel is becoming a binary. So we have to replace some corresponding functions in the host part. Instead of loading the kernel as a textual field, we have to loading the kernel as a binary field. So we have to manually edit the host programs to load the RISC-V binary instead. However, this is not a really heavy workload because we only need to modify the corresponding kernel load code. So, and for the rest of the part, we can just reuse it like some part like set kernel arguments and create command queues. However, although it is not really a heavy workload, we are still working on to remove any human involved in the whole process. So we are working on totally reusing the host programs as well on Vortex, on CUDA Vortex root. So this is the OpenCL Vortex root, but as we know, the CUDA is, in most cases, the most appropriate choice for the high-level program. So we put the CUDA Vortex root in the first priority. Then after that, we just compile the edited OpenCL host code and link it with the Vortex driver. And one thing to be noticed is in this step, we will just compile the programs executed on the host side. So in other words, we do not need to rely on any POCO compiler. We can just using the default system compilers, just like Clang or C++. So finally, we just executing the OpenCL host program compiled with POCO framework. And in this, for the host program, the POCO framework will executing some interface and link it as we link it in the Vortex driver. The POCO framework will using those driver to connect it with Vortex and do some fine-grained control for the Vortex device. So, okay, before looking at the CUDA root, as we mentioned before, as POCO, where our Vortex device can be executing on several backend architectures. So instead of in the real FPGA, we also provide some simulators for helping high-level programmers to debugging. So one of the most important SimX and also the most simplicity simulators is SimX. It is a simulator which simulates CUDA Vortex executions with C+ code. So it is really tiny simulators, but it aims to help developers to verify the correctness of the program very efficiently. So in the next section in our tutorials, we will provide some assignment which can help you to have a better understanding of the whole code base of the Vortex. So here is some major functions which is critical to implement the assignment file for our Vortex tutorials. For example, it has a decode functions, how to decode input binary instruction to maybe more fancy format to help to be parser in the future execution. And also execution part, which support cycle level executions to calculate the result of the input instructions and accordingly update the memory and register field. And here I put the screenshot of the commands how to executing a vector add example on SimX. And first, as I said before, we just compile it with POCO compiler. And then you can directly compile the host programs and link it with the Vortex driver. And finally, we executed the compiled host programs on SimX backend device. So for any other questions, we have another section for, especially for how to executing CUDA in the real case, in the virtual machine we just provide. So that is the introduction of the SimX. Okay, so now let's look at the most important part for CUDA on Vortex. As I said before, CUDA is the most appropriate choice for the state-of-the-art applications, especially for deep learning, reinforcement learning, and also some machine learning, or even for computer graphics. However, as I said before, our Vortex runtime is based on POCO, and POCO is just an implementation of OpenCL. But but CUDA cannot be executed with OpenCL framework. So it seems a challenge, but as I said before, POCO runtime can not only support OpenCL, but also support SPIR-V as input. So this gave us a chance to support CUDA on Vortex. So to support CUDA, we have to do an extra step compared with the original OpenCL. we have to first convert the CUDA into the SPIR-V, and then just input the SPIR-V into the POCO runtime and do the same things as OpenCL root. So before going into detail, I want to introduce some background informations. Obviously, we are now the first project want to executing CUDA on other backend device instead of the NVIDIA GPU. And there is a project named RISC-V. It's developed by AMD company. It tried to convert CUDA into HIP and then executing HIP on AMD GPU. However, this project using regular expression to convert CUDA into HIP, the front-end language used by AMD GPU. However, for most case, for most front-end language which can be executed on RISC-V, they do not have the same similarity between the CUDA and HIP. So we cannot directly using the same way as using the regular expression to convert CUDA into HIP. And another project, SQL, it is another high-level front-end language, and it can be used to compare to different backend device, also including some RISC-V backend device. However, it cannot reuse the existing CUDA programs. So instead, you have to re-implement those CUDA programs by the interface or APIs provided by the SQL. So from the best of our knowledge, our project is the first project which can supporting executing the CUDA source code on another backend device and without needed to change the CUDA source code. And another project I want to introduce is SPIR, or SPIR-V, the fifth version of the SPIR. It is critical for the scalable of our framework. So SPIR is an IR intermediate representation specific for high performance computing and parallel computing. And it can be regarded as an isolation between the front-end language and the back-end device. So with SPIR, we can compile a source code for different backend device. So in other words, due to the scalability of the SPIR, our framework can not only executing CUDA on Vortex device, but in future we can support executing G-Share or other front-end language on Vortex device. Maybe in future we can even extend the backend device. We can executing CUDA on other backend device like x86 CPU architecture. So now let's have a look of the major contribution. It is the NVPTS to SPIR-V translators. It consists of two steps. Our translator accepts CUDA source code as input. Then in the first step, we use the clone to compile the CUDA source code into NVVM-R. So NVVM-R is an intermediate representation proposed by NVIDIA, and it can just be regarded as a subset of LVM-R. And that after that, in the second step, we need to translate NVVM-R into SPIR-V-R. So for each NVVM-R and SPIR-V-R, it consists of three parts. For the device-independent instruction, such as load instruction, store instruction, or some really basic mathematical instruction like add and sub. So those instructions are exactly the same among all backend device. And another part is for NVVM built-in for device-specific built-in function. So this built-in function is different among all backend device. For example, although for both NVVM and SPIR-V is aimed for multi-thread, however, they have totally different built-in functions for high-level users to get the maybe block ID, thread ID, block dimension. So we have to take special care of those specific built-in function because it is hardware dependent. And also metadata information, which is used for code generation, it is also hardware dependent. Like it will require some specific information for the given hardware, like the data layout, the maybe 32-bit or 62-bit hardware address, or other things. So we have to specifically handle all those three parts. And for the first part, for device independent instructions, as it is common for all instruction, all the backend device. So in other words, for NVVM IR, it has the same instruction, but it's OpenCL IR. So we can using another third-party library for compile, for translate OpenCL into SPIR-V. However, for the NVVM specific built-in functions, they do not show in any other backend device. So we have to specially compile it with our own effort. So this is the major effort in our project. So finally, to verify the availability of our translators and whole Vortex architectures, we run some benchmarks on Rodinia benchmarks. And as you can see in our current versions, both in our translator and Vortex GPU, we can support most of those benchmarks. And there are some ongoing support benchmarks, but we can just support it after we supporting those some specific mathematic built-in functions, and also supporting those textual memory. So in other words, our Vortex has the capabilities to support all benchmarks in the Rodinia benchmarks. And I also conclude the current features support on CUDA on Vortex root. First, we support memory hierarchy. We can use constant memory and hierarchy shared memory. And other, we can support synchronization, like those barrier among the blocks or within a blocks. And most important things is we can support some mathematical operators like square root, log, absolute value. And those function is really critical to support some state-of-the-art models, especially in the deep learning community. Okay, so that's all. Thanks for your listening. And one important thing is we want to build all of our framework open source. So we have open source the modified POCO, our MVPTS to SPIR-V translators, and also our modified Vortex version LLVM on GitHub. So if you have any interest in any of this part, you can directly access the source code on GitHub. If you have any questions, and after this micro conference, you can just email me. And once again, thanks for your interest in not only for the CUDA Vortex, but also for the whole project of the Vortex. And yes, Professor, this is a whole for my introductions.
Okay, thank you, Marvin. Okay, so we'll have a short 10-minute break. So we posted the link to where you can download the VIA images or the instructions how you can get a temp account. I'm not sure how you get the password. Because, Dr. Young might post that information in the link, or you can just text us in a checkbox. So we're hoping that in a just a 10-minute break, you will download or have access to the Vortex GitHub repos that you can actually compile. And then after 10 minutes short break, we'll come back and we'll show a video of the running FPGA, and then also go over the tutorial assignment briefly and also explain the first solution. Okay. And then after that, we have conclusions, and then have a little bit open-ended discussions, and we'll be here in the Zoom section to help you until 1 p.m. And after that, we'll help you in offline. So we'll see you in 10-minute break, 11:55. Thank you. Jeff, do you want to explain about today's account?
Sure. Okay. As I say, if you give me, I'm getting a little bit of feedback. Okay. So basically, I posted in the chat the spreadsheet. It has the username. So I tried to pick everybody from the participant list here. And the password is the same for everybody. You'll SSH into this machine called Hawksbill. And if you look at the tutorial repo, let me share that as well. There is there's kind of an instructions page for how to get things set up. So basically, there's a just a script to kind of pull the version of the Vortex repo that we have. And I think it's already been built, so you can run some of the examples, and then if you want to try to modify it, then you'll have to rebuild some pieces of it. And I guess if you have questions, post in the chat.
All right, thank you. And next, our speaker is Liam. He's the senior undergraduate Georgia Tech. He's been working on us for about a year about running FPGA, Vortex on FPGA, and also helping with tutorial development. So Liam, can you try and share your screen and share the video? The first part is FPGA running a Vortex and FPGA, since we were concerned about whether it can really run. So we made a video. So only that part is a video, but after that, Liam will start give a live presentation about tutorial component.
Yeah, that's right. So I'll go ahead and show video now. Hi, I'm Liam Cooper from the Vortex team. In this video, I will demonstrate running Vortex on an FPGA. I'm logged into the server here at Georgia Tech. I'll be using this to connect to an Intel cloud server to run Vortex on an Intel Area 10 FPGA. This will be our target FPGA. The Intel Stratix 10 FPGA is also supported. So the first step, of course, is to download and build Vortex. So I'll run a git clone for the Vortex repo. When that is done, the user should install the various tools outlined in the Vortex README. So first we'll need to set some environment variables for the various tools we'll be using. These include environment variables for OPE, the RISC-V GNU toolchain, and for Verilator. So now that we have our environment set up, I'll go ahead and cd into the Vortex directory, and I'll run make. Okay, so now that Vortex is built, we will make a build for the FPGA using OPE. So we'll cd into the OPE directory, and we will run a make command targeted at the number of cores we would like to build Vortex for, as we can see in the make file. So Vortex is configurable up to 64 cores. For the purposes of this demonstration, I will be using 4 cores. So I will run make FPGA 4C. You may replace this 4 with 1, 2, 8, etc. up to 64 to change the core configuration. When the build is complete, the following file will exist in the build directory. This vortex_afu.gbs. So now that the build is done, we can check the log to see any possible errors. And as we can see, there were no errors in the tail of the file. So next we'll move on to signing the bit stream for this new build. This command uses the packsign tool from Intel's acceleration stack. Finally, we can program the FPGA. and the FPGA is now ready to run using the FPGA driver. So, I will now demonstrate some tests on the FPGA. These tests can be found in the tests/OpenCL directory in Vortex. So to start off, I will run a vector add test on the FPGA. Next, I will run the SGEM test, which is a single precision general matrix multiply test. Up next is the SaxPy test, which deals with both vector addition and scalar multiplication. And finally, I will run a test that solves a system of equations using the Gaussian elimination method. This has been a demonstration of Vortex running on an FPGA. Thank you for taking an interest in Vortex.
All right, and if you want to go over more steps of running Vortex on an FPGA, it's located in the Vortex docs. If you go to the Vortex repository and in doc, there's an MD file for FPGA setup. So now I'll go a little bit into the hands-on exercises. Share my screen. Okay. So again, please see our tutorial GitHub for the detailed instructions on these exercises. We're offering two different environments for these exercises and for testing Vortex. The first environment is contained within a VM. You'll install VirtualBox and Vagrant and download the VM image and a Vagrant file for the Vortex environment. You'll then import the Vagrant box image and start the VM. After booting, you'll do a Vagrant SSH to open the VM, and then source and set the Vortex environment variables and paths. And then you can test out Vortex. So these instructions are detailed in the VM README file, again in the tutorial GitHub. The second environment is a remote access environment. So for longer term use, you'll want to request an account for Georgia Tech's Crunch Rogues Gallery testbed. And details for that, of course, are on the GitHub. And so for this week, we have 20 temporary accounts for attendees to use. So you'll run this SSH command with the user micro21 and then your number in the spreadsheet that's being posted in the chat. Once logged in, you can set up the environment and download Vortex. You can use this source command or try with just the Vortex that's already installed on the system. And then you can make and test out Vortex. And once again, these instructions are detailed in the tutorial GitHub. So first try with the Vortex that's already installed on if you're already on the remote system. Okay, so now I'll explain a little bit about Vortex's black box. In the video, you may have seen me use a command using the black box script in the FPGA demonstration video. So this is the main script that we use for running tests under specific drivers and different configurations for Vortex. The arguments to the script are as follows. So you can specify the number of clusters, which is the number of processing elements, the number of cores, which is the processing element for containing multiple warps, number of warps, which is, of course, the collection of concurrent hardware threads, and the number of threads. You may also specify whether you want to enable the L2 cache among the cores or the L3 cache among the clusters. The driver argument is used to specify which driver to run the Vortex simulation. And currently there are 4 options. It's RTL-Sim, VL-Sim, SimX, or even on the FPGA, as we saw earlier. Debug is used to enable the debugging mode for the Vortex simulation. Perf is used to enable the detailed performance counters within the Vortex simulation. App is used to specify which test or benchmark to run in the Vortex simulation. Some of the main choices are demo, SGEM, and VecAd. You can see all the other tests. They're located in the Vortex. In Vortex, they're located in tests/OpenCL. The args argument is used to pass the additional arguments to the application that you run. So here's an example of usage if you wanted to run the SGEM benchmark using the SimX driver with configuration of 1 cluster, 4 cores, 4 orbs, and 4 threads. So now into the tutorial assignments. We made 5 of our tutorial assignments public on our tutorial GitHub. These tutorial assignments are designed to cover the different components of Vortex. Assignments 1 and 2's purpose is to introduce users to basic RTL development for Vortex. Assignments 3 and 4 introduce modifying the load store unit, as well as debugging Vortex. Assignment 5 covers adding new custom instructions to Vortex. For this conference, assignments 1 and 2 provide the steps to get the solution, while assignments 3 and 5 also provide a solution, as I will explain later. If you haven't gotten the Vortex tutorial GitHub link, of course, here it is. It's also in the chat box, I'm sure. So for assignment 1, the basic task is to add a new performance profiling counter for the average number of active threads per cycle. An overview for this for the steps for solving this assignment are to check if the instruction is being issued, count the number of active threads in the active thread mask, and divide the total number of active threads by the cycle count in the driver. Then you can test your results with the output of the demo program. For assignment 2, the basic task is to count the number of coalesced memory requests. Because GPUs generate multiple memory requests from the same wavefront, oftentimes there are duplicate memory requests across multiple threads in the warp. So we can combine these multiple memory requests into a single transaction. This is what memory coalescing is. The approach for solving this assignment is to increment the counter in the load store unit when memory requests in the other threads are the same, and making sure to only increment once per warp. And then you can again test the output of the program with, or the output with the demo program. So for assignment 3, the task is to add a simple next line prefetcher in the load store unit. The general approach for this assignment is every time a load request is computed, generate the next cache line address and send it to the data cache. Note that the request metadata must be stored somewhere so that the correct requested memory address is known. For assignment 4, you will learn how to verify the implementation of assignment 3 by using the debug trace to see if the prefetched requests are generated and used correctly. Assignment 5 is concerned with adding a custom new instruction. So for this assignment, the new instruction is used for prefetching. The general approach for this assignment is to add an intrinsic for the new instruction in order to generate a binary with the same instruction, with the new instruction, and then defining the new instruction in SimX, then extending the pipeline, namely the decoder, and modifying the load store unit to take in the new prefetch instruction, and finally developing a test to check the functionality of the new instruction. You'll learn how to debug this assignment using the kernel dump and the run log. So as for checking your solutions for assignment 3 and 5, you should see the solutions folder in the tutorial GitHub for an overview for each of the solutions, and then also the code for both of those solutions. So as for downloading and executing the solution code is formatted as Git pull requests. So for each of the assignments, you can do a Git fetch for their respective pull requests, and then a Git checkout. And of course, more details on this are outlined in the solutions folder on the tutorial GitHub. All right, so now I'm going to demonstrate my solution to assignment 1. So let me see if I can go ahead and share from this other. See. Okay, looks like that worked. Okay. So I'm going to go ahead and show off my solution for the first assignment. So if you want to open that assignment on the, of course, the tutorial GitHub, I'll walk you through it. So the excuse me, 1 second.
While Liam's doing that, sorry, I did make a typo, so please check your username. I'm going to paste an example in the chat here. So it should be micro21 _ user, and then whatever your number is.
Thanks. Okay, so yeah, I'll go ahead and just demonstrate my solution so far. So this again is the oops. Okay, I think that should be easier to see. So I'll go ahead and run this black box script that'll sort of demonstrate the output of my solution. So this actually isn't a true error, so you can just ignore it for now. So we'll wait for this to make. Yeah, let us know if you're able to log in on the for the remote access, or even on the VM if you got it to compile or even run, then let us know. That's good to hear. Good to hear. Seems we got a few people.
Yeah, sorry, I made a typo, so hopefully everybody saw that. Yeah, and basically I left out the 21 in the username.
Might be even more slower than usual because many people are logging to the system.
Yeah, it's definitely slower than usual. Oh, there we go. Okay. So you should get an output similar to this. So as we can see, we got an average threads per cycle at 0.27 for this particular demo. And you can see per core also, it has recorded the active threads per core. So your output should be similar to this. So I can go through the, I still have time, so I think I can go through the files that I've modified for this. So following along in for the first exercise, so the first file that we want to edit is the VX config file. So in this file, we wanted to reserve a couple of addresses in the CSR for our new performance counter. So down here, you can see under this comment. So I called it the npm active threads. And so because we're defining a 64-bit counter, so I've defined two 32-bit addresses for the active threads. So this counter will, so we reserve the space for the active threads to count the number of active threads. And so also another file you would want to modify is the CSR data. To actually add in this counter here. So yeah, you can see here the so we've added in this 64-bit counter. And so next, we want to add this counter into the performance pipeline interface. So and go to interfaces. So I've added in this in active threads counter into this interface. So the point of this interface will be to we'll use this active threads counter in the issue stage. So we need to put it in an interface so that it can it can relay the information back to the CSR. So I've gone ahead and put this into the interface. And so next we can start modifying the issue stage, which is where we'll count the number of active threads. So there are some details outlined in the assignment 1 file for getting some things from the interface, getting what we just defined from the interface. So I've went ahead and put in this register for counting the number of active threads. And initialized it to 0 here on reset. And so for this is basically the main point of the assignment is counting these the number of active threads per warp. So we can see here that I've basically just got a for loop that goes through the thread mask and counts the number of active threads. And so this is when an instruction is issued. So instruction is issued when these two are, when the iBuffer is ready and valid. So, and then down here we assign it to the active thread the active threads counter that we just defined in the interface. And so to get the active threads per cycle, we'll need to divide the number of active threads by the cycle count. And so doing this in hardware is expensive. Synthesizing division is expensive. So I took care of that in the driver code. So we'll go ahead into the to driver comment and in VX utils. And so went ahead and added a variable for, this is a C++ code. So went ahead and added a variable for the active threads. And so this get CSR 64 from the driver actually gets the value from the CSR. So we'll get the value of the active threads, and we'll set that. We'll go through each core and then add them up to get the total number of active threads. And then finally in the output, we'll divide by the number of cycles to get our answer. And so, yeah, I think that's just a quick walkthrough of my solution to assignment 1. If you need, of course, all these more details are in the assignment 1 file. I just quickly went over it, but yeah, so have a try for yourself. And I think up next is
Thank you, Robert.
Yeah.
Thank you, Leah.
Yeah, Dr. Kim. Thank you.
If you stop sharing, I will share.
Yep. Sorry. There we go.
Okay, so we'll be all online until 1 p.m. and we'll have a various way of contacting us. So I'm not sure actually which one would be the best. We are thinking that GitHub discussion board feature might be a good way of discussing. but we also have a mail list we set up, and also we have a mailbox that are come to us. So we encourage you to try out, and especially we'll run this temp account for this week. So please try out and let us know how it goes. That whether it is a good approach or not, we also know whether people can actually do it. Okay.